Welcome back, class, to another video on optimization. This is going to be, I believe, the last video on optimization officially for the week, and so officially it will be the last video for the course. However, I of course expect that over the coming week, I will still be getting questions that I can post office hours videos about, so by all means, if something comes up and you still want to know, I'm happy to talk about it. But with that being said, let's look at this question. So I have here this function y equals the square root of 9 minus x. The graph, I'm just telling you, looks something like this. And I want to know of all the points on the graph, which of them is closest to the origin, that is closest to the point 0, 0. So my thing to optimize here is distance. And so I'm going to call that capital D. And my constraint is, well, if I think about it, what is this distance? Well, this point is x comma y because it is x to the right and y up from the origin. And so really, this d here, it's actually the hypotenuse of this right triangle. And so what this tells you is that this distance, it's actually the square root of x squared plus y squared. That's the thing we're trying to optimize. This is if you want just the distance formula, if you are used to thinking about the distance between 2 points in the plane being given by this x1 minus x0 blah 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 formula. This is exactly that. But my constraint is that this point xy, it has to be pinned to this graph. And so the constraint is, well, xy is on the graph. When is xy on the graph? Well, xy is on the graph exactly when y is equal to the square root of 9 minus x. Okay, now this is super convenient in all kinds of ways, but one of the most convenient things about it is that it's already solved for y, so I can plug it in. So that is our next step, is to solve the constraint, but we've already done that. So next, we'll go ahead and plug in this into our formula for d. And so I'm going to get d is the square root of x squared plus the square root of 9 minus x squared, which is to say the distance is given by the square root of x squared minus x plus 9. That is our function. Notice how nice that worked out, because the square root of 9 minus x squared is just 9 minus x, which is where this minus x plus 9 came from. After we're done that, we now go ahead to the take the derivative step. And so I need to take the derivative of d, which is going to be d prime of x. Okay, and the derivative of square root, remember, is going to be 1 over twice the square root of the thing. So 1 over twice the square root of x squared minus x plus 9. But this is a function inside a function, so I need to remember to do the chain rule. So I need to multiply here by 2x minus 1. This 2x minus 1 is the derivative of x squared minus x plus 9. So again, this 2x minus 1, this is coming from the chain rule. And so if you want, you can go back and rewrite this out a little bit more carefully if you haven't done a chain rule question in a bit. And really, the biggest reason why I'm doing this section last is to give you an opportunity to review your derivative rules before we have the final, where there will be a lot of derivatives. So we continue on to this next page. So we're looking for the derivative. And so the derivative here is 2x minus 1 over twice the square root of x squared minus x plus 9. And I want to know when this is equal to 0. But this is a fraction, so I only need to look at the numerator. And so I get that I'm looking for when 2x minus 1 is 0, which is going to give me x is 1/2. And so that is my critical number, my place where the derivative is 0. And so to finish the problem, I have to look at the endpoints, so to speak. So when I'm looking at x, well, x can actually be as small as I want. So I'm going to actually write d of minus infinity here. That's if x was all the way over here. But in that case, the distance would certainly be infinity, right? If this point of intersection was instead over there, infinitely far that way, that would put me infinitely far from the origin. So that's definitely not the closest. The furthest to the right that I can go would be this point. And that point is not so hard to see, is 9. So I can calculate also d of 9. And if you want d of 9 is the square root of, well, this point here is 9 comma 0. So this is the square root of 9 squared plus 0 squared, which is 9. Okay, so this point over here is a distance 9 away from the origin. And so then the question is, what's the distance of this point when x is 1/2? What's that distance? Well, that is by our function, which is over here. By our function, this is the square root of 1/2 squared minus 1/2 plus 9, which is to say that this is the square root of 9 minus 1/2 would be 8.5, plus 1/4, which is 0.25. This would be the square root of 8.75. Note, this is way less than 9. In fact, if you wanted, you could check that this point up here, which I didn't have to check because it wasn't a critical number and it wasn't an endpoint. But this point is 0, 3, so that point is definitely 3 away from the origin. But this number is less than 3, so this is the closest distance that I can get. And so that means the point is 1/2 comma, and then the square root of 8.5. That is the point on the graph that is closest to the origin. Note, I got the square root of 8.5 by plugging 1/2 into my constraint. Why is that square root? Okay. Here's a different question. But this question is also about the graph of y equals the square root of 9 minus x. But now, instead of talking about making the distance between that point as short as possible, I'm going to now make this rectangle here under the point xy. And I'm going to ask, what's the largest area this rectangle could have? So then, if I ask that, my thing to optimize is area. Which, again, just like before, because this is the point xy, this rectangle is x wide and y high, so the area is, in fact, literally just x times y. And my constraint is that the point xy is on the graph, so that is exactly to say that my constraint is that y is the square root of 9 minus x. So the nice thing about these graph questions is that you already have this thing written as y equals blah, 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 and you don't have to think about it anymore. Now, let me try and sell you on something. I could just plug this y straight in here. But if I do that, I'm going to have to take a derivative of something that's got a square root in it and a product rule, and that sounds messy. Alternatively, I could pay the price of doing a little more work now, and instead of just plugging in y, I could solve this for x. And then there will be no square roots, and everything will be nicer. So I'm actually, even though I already have this solved for y, I'm going to go out of my way and I'm going to solve it for x anyway. And here's what happens when I do that. I get y squared is equal to 9 minus x. So then I get that x is 9 minus y squared. That is my thing solved for x. And notice 9 minus y squared is a much nicer formula than square root of 9 minus x, because derivatives of square roots are kind of nasty. Okay, so then I'm going to plug that in back to here, and so I will get that the area as a function of y is 9 minus y squared times y, which is to say it is 9y minus y cubed. If I take the derivative there, a prime of y, get 9 minus 3y squared. I want to know where that's 0. So that means I'm solving 3y squared equals 9. So I'm solving y squared equals 3. So that gives me y equals plus the square root of 3 or minus the square root of 3. But notice every point on this graph has positive y, even though, like, technically maybe I could think about the rectangles over here, although probably then that doesn't really make sense. So I'm going to cross this off, and so I'm going to let y equal square root of 3 be my critical number here. Okay, so I have to think about what's the biggest and smallest y could be. Well, I need to interpret this question. I should have said this specifically. I need this point x comma y to be in the first quadrant. So the smallest y can be is 0 when it's down here. And the largest y can be is when it's up here, which is 0, 3. So I need to figure out the area if y is 0, the area if y is 3, and the area if y is the square root of 3. As is a familiar theme that seems to come up a lot, if y is 0, then this rectangle has 0 height, and hence the area is 0. If y, on the other hand, is 3, then x is 0, and the rectangle has 0 width, and so the area is 0. If y is actually the square root of 3, well, then the area of the square root of 3, if I go back to my formula for the area, which was here, that was my a of y, then I'm going to get 9 times the square root of 3 minus the square root of 3 cubed. I'm going to simplify that a little bit. So this is 9 times the square root of 3 minus 3 times the square root of 3. So it is 6 times the square root of 3. And so anyway, all I really need to know is that's positive, so that's definitely the largest area. And so the largest area here happens when y is the square root of 3, which happens to mean x is 6. So xy is 6 comma square root of 3. And in that case, the area is, well, 6 times the square root of 3. All right, that's all for the official video lessons of this course. But again, please email me or post on the forum if you have questions about any of the homework as you get to it, and I'll post more videos. I expect probably there'll be at least a few questions about the homework associated with this last section. But go back and review it, because the final, which I'll go ahead and post an outline for and not in the not too distant future. Probably by the time you're seeing this, it's already posted. Check the KD site. But if you have any questions as you go back and review that stuff, the final is going to be cumulative, so you can go back and review stuff, make sure you're comfortable with the chain rule and all of the stuff we did with integrals and all of these various sorts of things. But that means for the last time, until next time, be well.